Assalamu alaikum. In this lecture, I will remind you with the electric displacement and solve some problems. Now we know that the boundary conditions that D suffers a discontinuity, which is equal to 4 by sigma. This can be written in terms of phi as epsilon 1 d phi by dn minus epsilon 2 d phi by d2, which is 4 by sigma, and the tangential component of the electric field is continuous, which can be written as phi is continuous. Now recall that the Gauss's law in this case is divergence equal 4 by rho. So D is epsilon E, for we'll take epsilon as a constant. We have curl E equals 0, which means that E equal minus a gradient phi. Insert this here, so we get epsilon the Laplacian of epsilon phi is minus 4 by rho. That means epsilon phi is this integral. Now divide by epsilon, which means that we have to replace the rho by rho over epsilon. Now let's take an example. A point charge located at the z-axis and embedded in semi-infinite dielectric epsilon 1 for z positive and the epsilon 2 for z negative. And then we have to solve epsilon 1 divergence A equal 4 by rho for positive C and epsilon 2 divergence E for negative Z. Now we'll use a method of image. The first we have to take an image for Q at Q prime and then calculate the potential for Z positive. This is R1 and this is R2. The image we located at minus T. So doing so, we know that epsilon phi now is a solution for it is Q over R1 plus Q prime over R2. I'll use cylindrical system of coordinates. Now for the negative, we have to put a charge Q double prime here and find the potential at point here and the negative Z. So in this case, again, we have epsilon 2 phi Q double prime over R1. So we have two expressions for phi, one for positive Z and one for negative Z. Now we have to match the boundary conditions at Z equals 0. That is the normal component of D, which is now continuous because there is no free charge, sigma is 0, and the tangential component of the electric field or phi itself is continuous at Z equals 0. So this is the first condition. Doing so, we get Q minus Q prime equal Q double prime. The second condition gives us 1 over epsilon Q plus Q prime equal 1 over epsilon 2 Q double prime. Now put these values Q prime, Q double prime in phi, we get the expression for the potential phi. Take the gradients, you can get the electric field. So this is the Q2 double prime and this is Q double prime. Once we solve these two equations, insert them back in phi, you get the required potential. Now for the distribution, for the bound charge rho b, which is minus the divergence b, which is 0, except at the location of the charge, the sigma can be calculated from B1 normal minus B2 normal as in this case. This is the fields of D. Now let's move to another example which is typical. For this example, one can ask, can we find the Green's function for this problem? The answer is yes, but I will leave it to you as a problem. Now the electric sphere here in with epsilon an external field, subject to external field along the z-axis. Therefore, we have potential there. This potential is minus a0 r cosine phi. Now this we have to solve Laplace equation inside and outside the sphere. So inside we get this form. The 1 over r form does not exist because it diverges. We don't have it now. So for the outside we have this term because we have field at infinity and plus this term which approaches 0. Now from this r goes to infinity, we can find b1 which is minus a0. In this case the phi out is given by this expression. Now we have to find al and cl's. We have to apply the boundary condition at the surface of the sphere. Now phi is continuous, gives us this expression and this expression. the normal component is continuous, also gives us this expression and this expression. Then solving these four expression, one can get A1 is given by this and C1 is given by this expression. For L does not equal to 1, all ALs and CLs are zeros in this case. Now back, write phi in terms of these constants, which is given by this, and for phi out is given by this form. Let's look at the phi in. Phi in, if we look at our cosine theta and substitute it as z, we see that E is minus d phi by dz. It doing so, which is the derivative for this is 1. So we get that a constant field inside the sphere. And this is the phi out. This is the last term, can be written as this form. Now the polarization B is the P over V. V is the volume of the sphere. This allows us to write what is the dipole moment of the sphere, which is this thing. In this case, we can get sigma from the polarization, which is minus P2 minus P1 dot N. This gives us this expression. Now for the last term of phi out, here I am showing in the slide that it's a contribution of a dipole moment. Thank you.